Lecture number 1, load tracing. So we want to start by going over the definition of force and reviewing the equations of equilibrium. What is force? Force may be defined as the action of one body on another that affects the state of motion or rest of body. Based on Newton's third law, for every force of action, there is a reaction that is equal in magnitude, opposite in direction, and has the same line of action. So, if we have a beam sitting on two columns, for example, we have a load on our beam, we calculate beam reactions. The load transferred from beam to column is equal in magnitude, opposite in direction, and has the same line of action. So again, if these two are end reactions of our beam, the load transferred from the beam to the column is the same magnitude, opposite direction, in the same line of action. The third law also introduces us to the basic concept of force and equilibrium. It states that whenever a body A exerts a force on another body B, body B will resist with an equal magnitude but in the opposite direction. Figure 2 shows ground resistance on a building. This one is when we have an equilibrium. What does it mean? It means that the load is equal to soil resistance. So there is no movement. Our structure is stable and in equilibrium. If structure load is higher than soil resistance, then we will have settlement. And if the load is less than soil resistance, then we will have levitation. Okay, so that was the definition of force and action and reaction. Now we want to look at different types of loads applied to a structure. So we have static loads and dynamic loads. Static loads are gravity type forces, weight of beam, weight of column, weight of rafter, weight of a structure basically. Dynamic loads are due to inertia or momentum of the mass of a structure. So we need to include all of different types of loads that are applied to our structure. All the following loads must be considered in the design of a building structure. This includes dead load, which we use DL to show it, live load, wind load, earthquake load, and a snow load. Dead loads, again, dead loads are loads resulting from the self weight of the building or structure. Or basically, it's any permanently attached component, such as partition walls, flooring, framing elements, fixed equipment. Any load, any type of load that is applied to the structure for a long period of time or a permanent load is considered a dead load. Loads that are transient and moving or applied for a short period of time are considered live loads. So we have dead loads and live loads. Example of live loads are occupancy loads, furnishing, storage, furniture. Any of these are considered live. Here in this figure, you can see examples of typical building loads. So we first look at the roofing system. We have a snow as an example of live load and roof materials and structure as an example of dead load. When we look at this section of the building, we have occupants, movable fixtures and furniture as live load. Dead load, weight of walls, floor, and materials and structures are examples of dead load. So we need to make sure that we consider all of the different types of live load and dead loads applied to our structure in our design. So we have dead load, we have live load, roof live load, floor live load, a snow load, wind load, and earthquake load. One more time, we need to include any type of load that is applied to our structure in our design. Now we want to design our structure. There are two different techniques. First one is called allowable stress design. What does it mean? It means that the actual stress in an element, in a beam, in a column, in our foundation should be less than or equal to allowable stress, which we calculate using properties of materials. So, one more time, the allowable stress design, it just says that the actual stress should be equal or less than what is allowable stress. We will use same concept to design foundation and to find cross-sectional area or width of our footing. And a reminder that stress is force divided by unit area. That's the difference between a stress and a force. A stress is when you divide force or load by cross-sectional area of your element. The second technique is called a strength design, and we have resistance factor times the strength should be equal or larger than sum of load factors times loads. So you see a main difference between technique 1 and 2 is that here we have a load factor and a resistance factor, which basically provides a weight. So the load factors here, and you see, instead of just adding all of our loads together, we multiply load by load factor, and then we add them together. So each load has a load factor, and we multiply our strength by a resistance factor. For our class, we will use this concept to calculate the minimum required width of a footing. So we have applied load from superstructure, from our structure, how much is transferred to our footing. Using information we get from soil testing, we calculate bearing capacity, allowable bearing capacity. This load here, the load applied from superstructure divided by area of our footing should be equal or less than allowable bearing capacity, which we calculate using properties of soil. So this is the one that we will use again in this class. Next thing that I want to review before we start load tracing is the calculation of resultant of forces. In this example, we have coplanar parallel force system. So we have F1, F2, F3, and F4, and we have the distance as x2, x3, x4, and so on. They're all in the same plane, and they're parallel to each other. This is the resultant. We want to calculate the resultant. Resultant force, or R, is equal to sum of all forces. So it's going to be F1, F2, F1 plus F2 plus F3 plus F4, and so on. One more thing that you need to pay attention is the direction of the arrows. So we have 3 downward arrows and 1 upward. So if we assume a negative sign for downward and a positive sign for upward, here we have minus F1 minus F2 plus F3 minus F4. That's our resultant. Now we want to, so this was a point load or a concentrated load. That's what we call a point load, and it's usually in pound. Now we want to look at the resultant of distributed loads. The resultant of a distributed load is equal to the area of the load diagram. It's acting at the centroid of that area as indicated. So let's look at 3 examples. The first one, we have a uniformly distributed load. So here is a beam and we show a uniformly distributed load like this. And the unit is usually pound per foot. So here we have a uniformly distributed load shown here. And the resultant, the red arrow, is equal to the area of this rectangle. The rectangle has this side is W0 and this side, which is the length of our beam, is L. So area of this rectangle is equal to W0 times L, which is our resultant. Again, the resultant of a distributed load is equal to the area of the load diagram. Here we have a rectangular load with 2 sides. One is W0, the other one is L. So the area is W0 times L. And then the resultant is placed at midpoint. So this is our resultant, which is equal to W0 times L, and it's at center of the beam. The second example is a triangular load. So the load diagram is a triangle in this case. Now we have a triangle. This is our triangle. And the resultant is equal to the area of this triangle. This side is W0 and this side is L. So our resultant here, this is our resultant, is equal to half of W0 times L. And it's placed at 1/3 from the base of the triangle and 2/3 from here. The third example is a trapezoidal. So now we have a trapezoidal load. We can do the area, use the formula to calculate area of trapezoidal, or we can say that we have 2 resultant. One is in the shape of a triangle and the other one a rectangle. F1 is W0 times L, rectangle, and F2 is half of W02 W01 times L. So these were examples of calculating the resultant of a distributed load. And the last thing that I want to review before starting the load tracing lecture is the equations of equilibrium. In a stationary systems, all forces acting on an object balance and cancel each other out. All moments acting on an object balance and cancel each other out. So if we have a beam which is in equilibrium, it means that sum of forces in all directions are equal to 0. Sum of moments in all directions is also equal to 0. Now let's look at a warming up exercise. Again, just to review how we can use equations of equilibrium. And this is again a review before we start load tracing. So we have a simply supported beam with uniform load. We have a beam, simply supported beam at ends, and a uniform load of 2000 PLF. PLF is pound per linear foot. The question is asking you to calculate point loads or end reactions, which is R1 and R2. So we are looking for these end reactions. In order to solve this problem, we can use sigma Fy is equal to 0. We have the resultant of the uniformly distributed load. It's a rectangle. The load is 2000 pounds per foot for a total length of 10 feet. So it's 2000 pounds per foot times a total length of 10 feet. Our resultant is 20,000 pounds. So we can say that we have 20,000 pounds pushing downward, and we're going to use a negative sign for downward. And we have two end reactions, R1 and R2. So I want to write down this formula. Sigma Fy is equal to 0 minus 20,000 pounds plus R1 plus R2 is equal to 0. This system is symmetric, which means that R1 is equal to R2. So now I can rewrite this formula and replace R2 with R1. We calculated the end reactions using the equations of equilibrium. We used a negative sign for downward forces, a positive sign for upward forces. We calculated the resultant of the uniformly distributed load, 2,000 pounds per foot, for a total length of 10 feet, which gives us 20,000 pounds. 20,000 downward, R1 and R2 upward. We calculated the end reactions as 10,000 pounds for each end reaction. Let's do another example. Again, warming up example number 2, just to do a review of statics, materials 2, and to see how we can use the equations of equilibrium to solve this problem. If you're interested, you can pause the video and try to solve the problem by yourself and then check your answers. So we have a beam. Reaction at point A and reaction at point B. We are trying to calculate these two reactions. The other load that we have is a uniformly distributed load of 10,000 pounds per foot for a total length of 13 feet. So we need to calculate the resultant, which is 1,000 pounds per foot times 13 feet. So it's 13,000 pounds. So we have a beam. We have 13,000 pounds. We are trying to calculate these two reactions. And again, this load is 13 divided by 2, 6.5 feet away from reaction point A, and this one is 10 feet away from point A. Another reminder that moment is force times distance. We're gonna write the formula for sum of moments around point A is equal to 0. So this is point A. We have a moment here caused by 13,000 and another one here caused by reaction at point B. We're gonna use a negative sign here and a positive sign for this moment. $13,000 times distance. with a negative sign. 13,000 times the distance of load 13,000 from point A. And then we have reaction at point B times distance of reaction at point B from point A. And as I said, we use a positive sign for sagging and a negative sign for hugging. So if you solve for RB, we have the reaction at point B as 8,450 pounds. So we had this 13,000 pound times the distance, which is 6.5 feet, and RB times the distance, which is 10 feet. Now we want to solve. So here we have the resultant, which is 13,000 pound downward. Reaction of B, we just calculate 8,450 pound upward. We need to calculate reaction at A. Downward, we use a negative sign. Upward, we're going to use a positive. Minus 13,000 plus 8,450 plus reaction at point A is equal to 0. And when you solve, you get 4,550 pounds for reaction at point A. Warming up exercise number 3. We are calculating point loads at point A and B. So we are again looking for reaction at point A and reaction at point B. We have the resultant here, which is 1,000 times 10 feet, so 10,000 pounds, and this one is 5 feet from point A. Then we have here 500 pounds, and this load is 15 feet away from point A, and then the third one is reaction at point B, which is 20 feet away. So this one, the moment is sagging, so we're going to use a positive sign. This one, around point A, the moment is hugging, we're going to use a negative sign. And here also it's hugging, so we're going to use a negative sign. So I'm going to write sigma MA is equal to 0. We have minus 10,000 times 5 minus 500 times 15 plus RB times 20 is equal to 0. And you can solve for RB as 10,000 times 5 plus 500 times 15 divided by 20. Then you need to write down sigma f y is equal to 0. So now we have this beam. Here is our resultant, which is 10,000 pounds. Here we have 500 pounds. Here we have reaction of B. And here we have reaction of A. Minus 10,000 minus 500 plus reaction of A plus reaction of B is equal to 0. And that's how you solve for reaction at B and reaction at A.